MCP servers are becoming a popular way to connect AI systems to real tools, data sources, and internal services. They're powerful, flexible, and easy to deploy, which is exactly why they introduce serious security risks when they're not designed carefully. In this video, I'm going to explain what MCP servers are, the security issues they often introduce, and how these problems show up in real environments, not as theory, but practically. MCP stands for Model Context Protocol, and it is a proposed open standard introduced by Anthropic. At a high level, an MCP server acts as a bridge between AI models like Moltbot and real systems. Instead of a model just generating text, it can call tools such as APIs, databases, and internal services through the MCP server. One example that you've probably seen by now is OpenClaw, formerly known as Moltbot, formerly known as Claudebot, the personal AI assistant that can draft emails, plan trips, create to-do lists, meal plans, and budget. You can connect it to WhatsApp, Discord, Slack, and more. It sounds great, but that means that MCP servers often sit in a very sensitive position. They inherit trust from both sides. The AI system trusts them to do real work, and the backend system trusts them to act safely. That combination is powerful and dangerous if security isn't handled correctly. Some companies have already taken action against these personal AI assistants, completely banning them from their networks. MCP and tools like OpenClaw feel very reminiscent of the early days of the internet when protocols were being developed without much thought into security. However, this isn't the early days of the internet. We have more knowledge. Recently, Koi AI published an article detailing the research into a malicious MCP server, calling it the first malicious MCP server in the wild. Koi's risk engine flagged an MCP server called Postmark MCP when version 1.0.16 was introduced. Postmark is an email delivery service specifically for transactional emails. It's automated things like password resets, account confirmations, receipts, and notifications. When Koi dug into the code of this Postmark MCP, they found a suspicious line that BCC'd an email address on every single email sent out from anyone using it. It turns out that there is a legitimate GitHub repo with the same name that is officially maintained by Postmark, and the malicious repo was a result of the attackers copying the legitimate repo and adding their malicious code and then publishing it under the same name, so unsuspecting users were downloading the wrong repo. Koi estimates that the MCP server was downloaded over 1,500 times every single week. That has huge impact. Another security issue to be aware of is overprivileged tool access. One of the most common issues with MCP servers is overprivileged access, and to make things work quickly, MCP servers are often given broad permissions to internal systems, full API access, wide database permissions, or cloud credentials that can do far more than necessary. In a real environment, this means a single MCP server might be able to read sensitive data, modify records, or trigger actions that were never intended. If something goes wrong, whether that's misuse, a bug, or unexpected behavior, the blast radius is huge. From a security perspective, this creates a highly trusted service that can be influenced by an external input, which should always raise red flags. Another major issue is weak or missing authentication. Many MCP servers assume that if a request reaches them, it must be trusted. Sometimes they rely on network location, sometimes on static tokens that never rotate, or sometimes on no authentication at all. In the real world, this means that if another system inside the environment is compromised, an attacker may be able to call the MCP server directly. And because the MCP server already has access to powerful tools, that attacker effectively inherits all those capabilities. If something can talk to your MCP server, it can often do everything your MCP server can do. Another security issue is prompt injection. Even when the MCP server itself is technically secure, it can still be abused indirectly through prompt injection. The MCP server doesn't understand intent, it just receives the requests and executes it. A blog from Sync says prompt injection occurs when an attacker crafts input that prompts the model to perform an unsafe action. Sync staff reacher Luca Brewer-Kellner shows a real-world example of a prompt injection attack using Claudebot. Luca wanted to get details of the claudebot.json file, which contains various tokens and secrets that would be interesting to an attacker. To do this, Luca spoofed their own email email address and asked Claude to share its claudebot.json file. The Claudebot responded with the file. In more broader practice, this can mean that user input can cause the model to call internal tools in ways that weren't anticipated. The MCP server sees a valid request and does exactly what it's told, even if the results are inappropriate or risky. This is where people get caught off guard. They secure the server, but forget that the models can be influenced in subtle ways, and the server doesn't know the difference between a legitimate request and a manipulated one. This leads us to another issue: sensitive data exposure. MCP servers often aggregate data from multiple sources like logs, configuration files, internal documentation, or operational data. If those tools return too much information, that data can flow straight back to the model and potentially expose to the end user. In real environments, you may see error message, debug output, and internal details exposed simply because no one stopped to think about how much data was being returned. Over time, this turns the MCP server into a conversational interface for internal information that was never meant to be exposed. Verbose error messages is a finding I often include in penetration reports because these errors can provide too much unnecessary information that attackers could potentially exploit. But now, you've effectively turned the internal systems into something that can be queried through natural language. And lastly, of course, I have to talk about the lack of logging and monitoring. Most MCP servers lack proper logging and monitoring. They are often treated like glue code. Sometimes they just connect systems together rather than like a security critical infrastructure that they are. There's often no clear record of which tools are being called by whom or how frequently, and without that visibility, misuse or abuse can go completely unnoticed. And when something does go wrong, there's very little data to understand what happened. You can't defend what you can't see, and many MCP servers are effectively blind. MCP servers concentrate trust. They sit between AI systems and real infrastructure, often with high privileges and very little oversight. That makes them a high-value target and a high-impact failure point if security isn't considered from the start. MCP servers aren't inherently insecure, but they need to be treated like production infrastructure. That means enforcing least privilege, adding strong authentication and authorization, carefully controlling what tools and data the tools return, and logging tool usage, not just errors. Most importantly, assume that models can be influenced even unintentionally, and design systems that have that in mind. As AI systems continue to integrate more deeply into real environments, MCP servers are going to become more common and a lot more critical. The teams that treat them casually are going to be burned. And if this video was helpful, please like the video, subscribe for more content, and let me know if you want a deeper dive into MCP hardening or real attack paths. I'll see you in the next video. Goodbye.